Hello. In this video, we are going to learn about the fundamental theorem of algebra. So first, what is the fundamental theorem of algebra? Well, the long definition says every polynomial equation having complex coefficients and degrees n, where n is greater than 0, has at least one complex root. So pretty much, if f of x is a polynomial of a degree n being any number, then there are exactly n zeros of the polynomial when all real and imaginary solutions are counted. Now, something I want to include here that I did not include on the slide, but I'm going to tell you out loud is, if a polynomial function has one complex root, it has to have two complex roots. They have to come in pairs. And we're going to see that in a example at the end, but it's called the complex root theorem, I believe is the actual name. That may not be the actual name, but it's a theorem about complex roots. So let's look at an example. We're going to find the number of zeros of a polynomial function. So I gave you the function f of x equals 2x cubed plus x squared minus 3x plus 3. So the first question is, what is the degree? And then that'll lead us to the number of zeros. Well, the degree of this function is 3. Therefore, the number of zeros is 3. That means once we find all the zeros, the real zeros, the complex zeros, we are going to have a total of 3 zeros. Now let's find all zeros of the polynomial. So the polynomial is f of x equals 2x cubed plus x squared minus 3x plus 1. The first thing we want to do is we want to list our p's, q's, and p over q's. Okay, this is going to be all possible real roots, because if we find the real roots, then we can find the complex roots. But we can't really find the complex roots until we find the real roots. So let's begin. Remember, our p's come from our constant. In this case, our constant is 1. So our factors of 1 are plus or minus 1. Now our q's come from our leading coefficient, which is 2. So in this case, our factors of 2 are plus or minus 1 and plus or minus 2. Now p over q, we have to put all of our q's over our p's. So we have plus or minus 1 and plus or minus 1/2. All of our q's over our p's. All of our p's over our q's. I said that backwards. P over q. Okay, so now let's look. We see that all possible roots are plus or minus 1, plus or minus 2, plus or minus 1/2. So now we know we listed and then we deleted any duplicates and only counted for the possible numbers that we saw. Okay, now using the factor/remainder theorem from the previous video, we are going to take each of our roots, possible roots, plug them into the function and see which one gives us 0. Because we are trying to use the factor theorem. If we get 0, then we know that that is a root of the polynomial. So let's begin. When we plug in 1, we get 1. Okay, that is not a factor. When we plug in negative 1, we get 3. That is not a factor. When we plug in 2, we get 15. Not a factor. When we plug in negative 2, we get negative 5. Still not a factor. When we plug in 1/2, we get 0. So we know that 1/2 is a root of f of x. When we plug in 1/2, we get 5/2. So we know that the only real root that we have is 1/2. I don't know what just happened there. Okay, that's what it was supposed to look like. All right, so now what we're going to do is we're going to use synthetic division. So in this lesson, we are really taking everything that we've learned and we're putting it together. So we know that we want to divide this function by 1/2. Okay, the function was 2x cubed plus x squared minus 3x plus 1. And remember, for synthetic division, we have to account for every power of x. So we have squared, 2, 1, 0. And we're going to list our coefficients so we can divide. So we have 2, 1, negative 3, and 1. We weren't missing any powers, so we didn't have to put a placeholder of 0. Remember, our first step is to bring 2 down. And 2 times 1/2 is 1. 1 and 1 is 2. 2 and 1/2 is 1. Negative 3, I don't want that dot there. Negative 3 and 1 is negative 2. 1/2 and negative 2 is negative 1, and that is 0. So now we know that we have x minus 1/2. I'm going to show you a different way to write that in just a second. And then we have 2x squared plus 2x minus 2. Okay, now what we need to do is we need to solve this. Guess what we're going to use? Negative b, plus or minus square root, plus or minus square root, b squared minus 4ac, b squared minus 4ac all over 2a, all over 2a. Because we're looking for complex root, guys. We know that 1/2 is our only real root, meaning that the other two roots, because we have to have a total of 3, are complex, and the quadratic formula is what allows us to find complex roots. So, we have negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, so whenever we simplify our square root, we are going to get 2 square root of 5. So we have negative 2 plus or minus 2 square root of 5 all over 4. And we have negative 2 and 4 and 2. They're all even numbers. We can reduce each of these. Oh, I don't like that. You can't see it. Let's do this. We can reduce each of these by 2. So we have a negative 1 plus or minus 1 square root of 5 all over 2. Now you know that you do not have to write that 1 right there. Don't have to write it. So earlier I misspoke and I said this is going to be a complex root because I really thought that that was the example I picked. But I didn't. This is an irrational root because it has a square root. So 1/2 was our only real root. I mean, it was a real root. Our only rational root. And then we have 2 irrational roots. So all 3 roots are 1/2 and then negative 1 plus the square root of 5 over 2 and negative 1 minus the square root of 5 over 2. That is 1 root, 2 root, 3 root. And we were supposed to have 3 roots. So that is how you find all roots of a polynomial. Oh man, hold on. I went backward somehow. We're getting there. Give me just a second. Okay, example 3. We want to write a polynomial with the given zeros. 3, negative 3, 3 minus 2i. So we have a complex root 3 minus 2i. And earlier, remember, I told you that they have to come in pairs. So if we have 3 minus 2i, they have to come in conjugate pairs. 3 minus 2i, our other root has to be 3 plus 2i. Okay, remember conjugates, just change the operation in the middle. So we're going to begin writing our polynomial. So we know that we have to change the sign. So it's going to be f of x equals x minus 3, x minus negative 2, x minus 3 minus 2i, x minus 3 plus 2i. Now we need to distribute all of these negatives, so that's going to simplify to f of x equals x minus 3, and then a negative times a negative is a positive, so x plus 2. A negative 3 and a negative 2i is going to become negative 3 plus 2i. And then the negative times the 3 and the negative times the positive 2i is going to become negative 3 minus 2i. Now, guys, here is my piece of advice for you. You are always going to FOIL together, or not really FOIL, distribute your 2 sets of parentheses that have i's in them because something really awesome is going to happen. So x times x is x squared, x times negative 3 is negative 3x, x times negative 2i is negative 2ix, negative 3 times x is negative 3x, negative 3 times negative 3 is a positive 9, negative 3 times a negative 2i is plus 6i, 2i times x is a positive 2ix, 2i times negative 3 is a negative 6i, and 2i times negative 2i is negative 4i squared. Now, watch this. See what happens. We have a negative 2xi and a positive 2xi. Those subtract to 0. We have a positive 6i and a negative 6i. Those combine to equal 0. Now, so our i's are slowly going away. We need to combine like terms. We see we have a negative 3x and a negative 3x, so it's going to be negative 6x. So x squared minus 6x plus 9 minus 4 times the negative 1, because we know that negative I squared is negative 1. Negative 4 times negative 1 is a positive 4, and 9 plus 4 is 13. So now we have finished FOILing out or distributing x minus 3 plus 2i times x minus 3 minus 2i. So we're finished with that one, and now we need to combine x minus 3 times x plus 2. When we distribute, we get x times x is x squared, x times 2 is 2x, negative 3 times x is negative 3x, and negative 3 times 2 is negative 6. Combining like terms, x squared minus x minus 6. So we're going to take x squared in the first set of parentheses, and we're going to multiply it by x squared, negative 6, and 13. And that's going to give us x to the 4th minus 6x cubed plus 13x squared. Now we have to move to the negative x and multiply it by everything in the second parenthesis. So that's going to give us negative x cubed plus 6x squared minus 13x. And lastly, we need to multiply negative 6 by everything in the second set of parentheses. So it's going to be negative 6x squared plus 6x minus 78. Combining like terms, we see we have a negative 6x cubed and a negative x cubed. So that's going, and we have an x to the 4th in front. So that's going to be x to the 4th minus 7x cubed. Our next set of like terms are 13x squared, 6x squared, and a negative 6x squared. That's going to equal 13x squared. And then we have negative 13x plus a 36x. That's going to result in 23x. And then we have the plus 78. That there is our polynomial with the roots 3, negative 2, 3 minus 2i, and 3 plus 2i. So that concludes this video on fundamental theorem of algebra.